Hello once again. So this time I was requested to provide some clarification on the notions of Euler and Hamiltonian paths and circuits. But to begin with that, let's start with a few definitions. So let G be a simple graph. Let U and V be elements of the set of vertices of this graph. Also, let n be a non-negative integer. So a path of length n from U to V is a sequence of vertices and edges as indicated by these relations that we have here. So in the graph itself, I should have an edge joining U0 with U1, and I should have an edge joining U1 with U2 with this particular labeling, right? It might be different depending on the graph that you have. We would say that if the first element of the sequence and the last element of the sequence are equal, then the path is a circuit. Essentially, we are just returning to the same place. Whenever there are no repeated vertices, we would say that the path is simple. And on top of that, a cycle is a circuit that has no repeated vertices, except possibly for the first and last. So once we have that ready, we're ready to start with the definition of an Euler path. So an Euler path or circuit is a path or circuit where each edge occurs exactly once. And in a very similar fashion, we would say that a Hamiltonian path or cycle is a path where each vertex appears exactly once. Okay? So again, these definitions might be a little bit dry. Let's start with an example. And also some computational mechanisms to find such paths. Okay, so I'll start with this. Say that I have the following graph. Just like this one. And well, immediately becomes obvious that this graph has a Hamiltonian cycle. Which one? Well, look, if I start just from the labeling according to the enumeration that is indicated here, from 1 I go to 2, then to 3, then to 4, then to 5, then to 6, then back to 1, I construct a cycle where every single vertex appears exactly once, except for the first and last. So this is a cycle, and it's Hamiltonian. Now, what about an Euler path or circuit? Well, let's see. What if we do the following? What if I start at this vertex? The intention is to be able to cover every single edge. So let's start with the following process. If I start at 2, right? Then, for example, I may go to 3. But then from 3, I may go to 6. From 6, I may go to 5. Then here I may go to 4. Here I may go to 3. But then, look, once I do this, I get stuck here. So I have to backtrack. Say, okay, well, maybe this wasn't a very good choice. So instead of going directly into 4, I can go to 3. But then I'm actually forced to go to 4 and then go to 5. So I have to backtrack. So, well, that wasn't a good choice. So, nah, not that one. Okay, so backtracking. When I am at 6, I shouldn't go to 5. So where can I go? Well, I can go to 1, and then I can go to 2, but then I get stuck. Okay, well, that's it. That means that I shouldn't go neither to 1 nor 5 from 6. Well, where else can I go? I can go to 2 and then to 1, but then I get stuck, right? Well, that means that maybe taking this choice wasn't that good. So I'll backtrack and see, well, where else can I go from 3? Well, from 3, I can go to 4, but then to 5, but then I get stuck here, right? Well, what else can I do? Well, from this one, I can go now to 5 and then to 4, but then well, I get stuck once again. That means that we shouldn't go in this direction if we are. Well, let me do the following. So now from 2, then to 6, to then then to 3, then to 4, and then to 5. And now, if I was to signify this with colors, just to make them much more remarkable, let's see, what is this indicating to me? From 2, I go to 1. Then from 1, I go to 6. Then from 6, I go to 2. Then from 2, I go to 3. Then to 3, I go to 6. Then from 6, I go to 5. Then I go to 3, then to 4, then to 5. And there we go. If we start just from here, we will finish here. And we have used every single edge exactly once. So in this case, we have constructed an Euler path. This is not a circuit. It starts and ends at a different vertex. So what about Hamiltonian paths or cycles? Well, take another example. This is what we call a cube, a Q3. And well, to have an implementation of this, we have the regular form of a cube as usual, as usually represented. But now this time, I'm going to make the following implementation. I'm going to indicate vertices by strings of length 3, binary strings of length 3, where every 2 strings are adjacent when they differ by 1 bit. So I have something like this, 0, 0, 0 here, 0, 1, 0, 1. For this one, I have 0, 0, 1. For this one, I have 1, 0, 0. For this one, 1, 0, 1. For this one, 1, 1, 1. For this one, 1, 1, 0. And then you would say, oh, look, what if I follow this path? Starting, I'll move in this direction, then in that one, then in that one, then to the back. Then I'll keep that one, then that, and finally there. So what if I represent this using a sequence as we should do it in formally, where we will go like this. So I'll start at 0, 0, 0. Then I move to 0, 0, 1. Then I move to 0, 1, 1. Then I move to 0, 1, 0. Then I move to 1, 1, 0. Then I move to 1, 1, 1. Then I move to 1, 0, 1. Then to let me know in a comment if you'd like me to go over this particular topic. Now, but what we have here is a Hamiltonian cycle. But the question is whether this graph has an Euler path or circuit. Well, the short answer is no. Because there's a theorem that associates the existence of an Euler path or circuit and the parity of the degrees. In other words, for a connected graph to contain an Euler circuit, every single vertex should have even degree. Fair kind of like intuition is that every time that you go and visit a vertex, you should be able to go out, right? This using a different edge. For the existence of a path that is not a circuit, well, same conditions in terms of connected graphs. You should have all of the vertices of even degree except for two, which would be the initial and the final vertex of your Euler path. Now, you may say, well, okay, we can leave that for a secondary video if you like to. Now, here's an example of a graph that has no Hamiltonian path. Okay. So how do we start? Well, this time I have the following picture. And I'm going to label this as A prime, B, C, and C prime. The primality essentially for the symmetry associated with the picture. Now, once again, the intention here is to demonstrate that this graph that we have presented doesn't have a Hamiltonian path. Well, for that, I have to start somewhere. So let's say that I start at A. And you say, well, where can you go from A? From A, I can go to B. And then you may say, well, from here, you can go to A prime, but then you get stuck. So we shouldn't use that one. You may say, well, from B, you may also go to C. But if I go to C, what would happen? Well, I will be forced to go to C prime, and then I get stuck because I will have to visit B. So I shouldn't follow this path. Now, something similar happens if from B I follow the path that goes to C prime and then to C. I will get stuck. Well, that's it. I cannot start at A. So similarly, I cannot start at A prime. Now, what if it starts at B? Well, if we start at B, then I have the following options. I can go to A, but then I get stuck. Well, I can go to A prime, but then I get stuck. I can go to C, but then I need to go to C prime, but then I get stuck. Well, that means that I can also get from B to C prime, but then for the similar reasons, I will get stuck at C. That means that I shouldn't start at B. Well, what if I start my path at C? So if I start at C, right, what may happen? Well, here I have, I can go to B, and then from B, I can go to A, but then I will get stuck. Or from this B, backtracking, I can go to A prime, but then I get stuck. That means that I shouldn't go to B. So from C, I can go to C prime. But from C prime, I must go to B, and then, well, I get stuck. That means that I cannot start at C. And similarly, for C prime. Well, essentially what we have done here is to exhaust all possible paths that could be Hamiltonian. So there are no Hamiltonian paths whatsoever. But but this was an exhaustive search. Here's a question. Is there a simple, and I'm going to put that in quotation marks, way to determine if a graph contains a Hamiltonian path? Well, I leave that for the comments in a subsequent video. I hope that you enjoy it. Take care.